Okay, and now for the last part of today's lecture, the boundary tag allocator. The boundary tag allocator is by far the most complicated of the various types of allocations we're going to talk about. And it's complicated enough that I'm not going to ask you to write one. I won't ask you to write one during the exams. I won't ask you to write one in the labs. I might ask you questions about them, or ask you to perform some small part of the algorithm on an exam or something. But the boundary tag allocator is the general purpose allocation format. If you want to write your own allocator and bypass Windows, as I suggested in the beginning, what you're probably going to want to do is ask Windows for just all memory. You're just going to say, give me all the memory I'm going to need. I just want 5 megs. 5 megs? What the heck? 5 gigs. Give me 4 gigabytes of memory. Give me however much your system can give you. Give me that memory. And then you're going to parcel that out on your own. And from now on, when the users want to allocate memory, we're going to allocate from this big block we got. And some of you are thinking, well, wait a minute. You said we weren't going to use Windows, and now you say you start off by asking for Windows. What I mean is I won't use Windows in real time while the game is running. When the game first boots up, I'll make an allocation right at the beginning, say just give me all of it. And now I'll manage it myself from then on. So that's something we could do in a Windows system, or more likely you'll do this on a console where you know how much memory that console has, and you know that you have exclusive access to the console and all of its resources. So you're making yourself a Nintendo game on the latest Nintendo hardware, and you look at the specs, you know how much memory it's got. You'll ask for as much of it as you can possibly get. The operating system will reserve some of it for itself. So you just ask for as much as you can have, and then you'll parcel that out on your own from now on. So in real time, while the game is running, you will not need to go back out to the operating system to get memory. You're going to use your own manager. And what you might want to use is something called a boundary tag allocator. So I'm going to go through it very briefly, give you an overview, and let me just give you a tip. I have seen in recent years big name local companies who give this algorithm as their take-home engineering interview test. So there are people out there, and they're some of the top tier employers, really. They're some of the top tier game companies who expect their programmers to be of the caliber to handle writing this fresh out of school. So if you want to go for one of those types of jobs, if you want to be a Naughty Dog or an Insomniac, that's the kind of hardcore programming you should prep for. And so that's what I'm going to go through right now. If you're thinking more along the lines of, I want to make Unity games, why are you breaking me here? That's okay. Watch the algorithms, understand how they work, but I'm not going to ask you necessarily that everybody has to do this. It's not for everybody, but if you want to be the hardcore and you want to go for those positions, be prepared for something like this. All right, let's take a look at the boundary tag allocator. The boundary tag allocator is a general purpose allocator. It's for when you don't know how big the allocations will be, and you want to allocate them in any arbitrary order. So we can't use the stack because we don't know that they go in and out in a particular order. We can't use the pool because we don't know how big those allocations are going to be. So we are going to try to minimize the wasted space the best we can, and we're going to try and do it in a very efficient way that involves like a limited amount of searching, and try to go quickly with our allocations. So what we're going to do with the boundary tag allocator is we're going to, like everything else, we're going to split up our individual memory allocations into blocks. The thing though about this algorithm is our blocks are an unknown size. So what we're going to do is tag the boundaries of our block. We'll tag the beginning of the block, and we'll tag the ending of the block with some data. So what I'm suggesting here, for example, is we'll put 4 bytes for the size of a block, and then maybe a pointer to the next available block. Then comes some just unknown size of data, and then at the bottom of this block, we'll put another tag for the end boundary. And so we'll repeat the size there, and we'll see why here in a minute. Repeat the size, and we'll have a pointer the opposite direction. So now we have a double linked list, a linked list that goes both ways. So we'll have a forward pointer and a backward pointer, which we're kind of going to need, or at least it will help optimize this routine to make memory access quicker. You might notice that I've put in 4 bytes for the size, so that means my individual blocks cannot be 4 gigabytes each. So I'm imagining that no one would ever allocate in a single block within my game engine anything that large. So I'm saving some bytes by making the size a little bit smaller. Another trick is I could say that no size ever has an odd number. Maybe it does. Maybe every size is some multiple of 4. So the least significant 2 bits of my size, maybe I could use those, I could chop those off, and that would give me a larger number with just 4 bytes. That's the kind of thing I would want you to consider as you are thinking about this boundary tag. Is one of the things we want to do is try to squeeze out the number of wasted bytes. If you see this on like a take-home interview test, they're going to make a serious consideration for that. So that's one of the things they're going to want you to be thinking about. So let's talk about creating our boundary tag allocator. What are we going to do? For example, what we're going to do is we're just going to get a big old block of memory from somewhere. Maybe you initialize that, with some memory you got from Windows, or maybe it's a static array or something. And then we're going to put the tags at the beginning and the ending of a block. For example, let's show an example of a 1K allocator. It's a very small allocator, but it shows the example of what we need. We'll start off with our 1K, and all of it is one big free block. Right now, from the beginning, we haven't allocated anything, so it's all available. It's all one big block. So we'll tag the beginning with the size. We'll put the next free pointer. Well, there are no next pointers, so that's a null. Then comes our unused bytes. Put the null again for the previous free, because there are no other blocks, and then repeat the size again, 1000. Now, notice I said it was a 1024 allocator, or it's a 1024 byte, I should say. There's a 1024 block, but we didn't end up with 1024 bytes available. We had to burn 24 of those bytes on our accounting. The tags at the beginning and the end are sucking up 24 bytes, leaving us only with 1000 bytes to work with. That's that wasted space. We do want to try to minimize that. So what happens when the user asks for some memory? Let's allocate 256 bytes. What we're going to do now is we'll split our tags into 2 blocks. The block that contains the user's 256 bytes, and then the rest of it is still available. So we had 1000 bytes to work with. We are going to split that 1000 bytes, and I'm showing splitting it so that the user gets the bottom part, and we're showing the top part is free. So what do? We say, okay, we need to reduce the size of this last block to 256 bytes. And then we've got our pointer, and then our 256 bytes, and then our pointer, and then we need to fill in, this is the top tag. This is a new tag that needs to get inserted into the middle there. So from the bottom where we were, we split it, resize it, back up one pointer, back up 256 bytes, back up, there's our pointer, back up, there's our 256 bytes. Now, For our pointers, this block is not in the free list. So I'm using a magic number here of 1. I'm putting a 1 in both the free and both the next and the previous free to indicate this is an allocated block, which if I walk through my blocks one after another, I'm going to find that this one is in use. I'll need to ask that later on. I'll need to ask whether it's in use or is it a free block. And I can tell that it's an in-use block because it's got an illegal address. There's no way that's a legal pointer. So because of that, and it's not a null. It's not a null, so it doesn't mean it's the last one. And it's not a legal pointer, so that doesn't mean that's where the next free block is. That's what I'm doing there. So after I've carved off my 256 bytes and put in my header, then I need to put in the footer of the previous block. And that would be 720 bytes is left after I pulled out from my 1,000 that I had. I pulled off 256, and then I pulled off the extra tag. So that left me just with 720. And I'll fill in my next free pointer and my last free pointer, which are still null. This is the only free block, and that's indicated by the next free and the previous free. Okay, and like with the pool, I have a pointer to my first free element that's going to point me right here to this first block. Okay, let's allocate some more memory and see how that goes. Okay, now let's say I'm going to allocate 128 bytes. I'll go to the free list, go to the top, and I'll find that I had that 720. That's big enough to give me the 128. So I'll split that 720 block. These two used to be a single 720 block. I'll split it, and I'll take the bottom 128, give that back to the user, adjust my footer, insert my header, and then insert a new footer for the block that was reduced. Now, that's how we allocate a block. How do we free a block? Okay, to free a block, we may need to combine the two blocks together. When we free a block, we might find that after having been freed, it's now adjacent to another free block. If two free blocks are adjacent, we want to combine them into a single free block to minimize the fragmentation problem. Let's see how that might work. Let's free our initial 256 byte block. Here's what we do. The user says, hey, free this. What are we going to do? We're going to go back up by 1 pointer. That should be the magic number. Maybe we'll confirm, is the magic number there? And back up from there, and that'll tell us how many bytes that was. The user won't tell us free the 256. They'll say free this address. So from this address, we back up. There's our magic number. Back up again, and that's the size of that block. That tells us where to find the footer. So now we know how big this whole thing is. We know where the next free pointer goes, and we know where the previous free pointer goes. So we have to insert ourselves back into the list. So we have to find what the address of the previous free block is. How do we get that? Well, this one's going to be a bit brutal. We'll have to go to the free list, start at the free list, and follow its pointer down through until we find the next available block. What we're going to find, though, is that was null. That was null, and so this is the previous free block. So this is the previous free block here, and so we can just make a linked list between these two. This one points to our most recently freed block, point to that as the next free, and this one's next is null. This one's previous will point backwards up to this one, and its previous can stay as the null that it is. So now we have a linked list. If we see what we've got here, starting from the top, we have a linked list. The first available block is this 568 block. The next one is this 256 byte block. And then the next one after that is null, saying that's the end of the chain. And we can then point backwards, and maybe we'll have a tail on here, pointer too. We can go backwards. So the last one is this, the previous points back up to the first one, and its previous is a null. So that's the end of the chain. So there you go, we're done, we've freed it. If somebody allocates again now, if they allocate something less than 568, they can have this block. If they allocate something less than 256, they could have this block. Let's see what happens now as we free the 128 block in the middle. The user is going to give us this data pointer to free. What do? We go back up in front of that one pointer, and we should verify that the magic number is there to make sure they're freeing something that has been allocated. In front of that is the tag that says the size of this block. So we now know how many bytes the user is trying to free. If we go in front of that, that tells us the size of the previous block. And one more in front of that is that pointer. Now, if that pointer is the magic number, that would indicate that's a used block. We'll have to keep searching up to find the next available block above us. In this case, it's a null, which says this is an available block. So we now know the previous block to us is that, and we can hook this up into the doubly linked list just by inserting it into the double linked list now. We know where it goes in the list. So we would mark this as the first block points to this block, this one points to the next block, and then the backwards pointers are hooked up all in a line. But notice what has happened here is that we have adjacent free blocks. We have an adjacent free block here and an adjacent free block here. We're going to want to collapse those blocks into ultimately a single block. First, let's collapse the lower block and see what happens there. We take the 128 byte block and the 256 byte block that was below it, combine them as a single block. So we update the size of the block and fix up the pointers and add the sizes together. So now we have 396 available, and we just have to fix up that the next pointer here was still correct. It was pointing to our header, so that one's fine. But the back pointer here needs to be fixed back up to point back up to what used to be the back pointer of that node. And that allows us to collapse that node into two. But then we notice that we have two adjacent nodes still, and so we can collapse those two using the same technique. We'll collapse the 568 with the 396 and end up with now only one node left, and it's back to our original. And we have not lost any bytes in the process, and we have not caused a permanent fragmentation. So that's sort of an overview of how the boundary tag allocator works. The main key, the big takeaway here is we set up a doubly linked list, a linked list that goes forward and backwards, and we put the size of each free block at both the top and the bottom of that block. The reason we did that was so that we can work our way backwards. If you go in front of your own allocation, you can see how big the previous block is. That'll allow you to work up forward from that, backwards again and backwards again, to find the previous blocks in front of you, or walk forwards, of course, through the headers. And that little trick of putting the tag at the top and the bottom allows you to go both ways through memory, so that you can then collapse when two blocks are adjacent to each other and both are freed. You want to collapse them. Take their next pointers, take the next pointer of the top one and point it to the bottom one's next pointer. Take the previous pointer of the bottom one and point it to the previous pointer of the top one, and now you've combined them as a single thing. Just add together the memory on the top and bottom, and now everything in between is one big block. And remember, when you free the piece in the middle with an empty block above it and an empty block below it, you're going to want to collapse both ways. Like you collapse the bottom and you collapse the top, and now you've got one big block continuous in there. Okay, so hopefully that was fun. It's a very high level look at it. We didn't look at how the code would be implemented, but I do think you might see something like this on a take-home, perhaps. Not something I want to get to in this class because, as I pointed out, it is kind of a pile of code to write. But that's how we do it. Okay, that's it for this class. I'll see you in class for the next lecture, and I'll see you online.